morning show on Netflix that we watched.
I saw that too.
Yeah, we really
I liked
liked that
that
one.
one.
All right, we're
Actually, I mean,
live.
I've been to that glass museum actually.
Oh, really? That's a real place.
Yeah,
Oh,
the
okay.
Corning Glass Museum in
Yep, I've been there.
upstate New York, Finger Lakes region.
Oh, that's
It's
cool.
very cool.
All right, we are live just in case you felt like you needed to say really inappropriate things. Everybody say hello to us before we begin this week's episode. And just a reminder to everybody, we have a pre-recorded interview, so we're going to do the news portion first, and then we're going to go into the pre-recorded interview. Ooh, and I forget how long my interview is. Hold on. You'll see me in a second here.
Either it'll be really
it's
long,
long.
show,
It's
or
27
really
minutes.
short
So
show.
let me just
It's 27. Wow.
yeah, so let me
So we should talk fast.
you know what? I don't think we have a lot of news, which is something that we're going to need to talk about.
Kim, is that a Pluto and Sharon plush
It
behind you?
is. Look at that. Look at that. It's Pluto
Nice.
and Sharon. I decided I want to get the whole set eventually, but I started with this one because it's 2 for 1. You know,
And they're
and they're
magnetic.
friends. They're magnetic. They go together.
Oh, are they
Great.
magnetic?
Yes.
Oh, that's awesome.
Yes. It's great. Yeah, they just sit back here. Buddies. Little celestial buddies.
So what are people, we were just before the show, we were all talking about the shows that we're watching. But if people want to chime in on interesting things that we're watching, I don't know. I was expecting to have like just a ton of free time on my hands, but because this quarantine life is not that different from my regular life, and
Yeah.
any free time that I have now is just spent sort of in an anxiety spiral.
I understand.
Yeah.
Yeah, I'm very thankful to still have my job. I can work from home 100%. I have been for like the past 3 weeks.
Yeah.
Um,
Yeah. And so, you know, I'm
yeah,
so
it's
it's
just
kind of the same.
never ending.
I just like I did before, you know, sat down, have a cup of coffee, look at a couple of news stories, play some video games, talk to my friends, do a show, go to bed.
I mean, I still have a 9 to 5 job. I
Oh,
just, you know,
right. Yeah.
changed from my night pajamas to my day pajamas.
Right. Yeah.
And
Yeah.
there you go.
I'm going to say hi to a bunch of
New
people.
coworkers.
Hello to Andrew Planet, Andy Cowley, Ben Kalo, Bob Moeller, Brexit Denier, Colin Edwards, David Fairweather, Eric Schneider, Ian Farquharon, Johnny J, K Spence 303, Larry Beckham, Miguel Angel Romero, Nancy Graziano, Paranor, Roger Haskin, Scott Bragdon, Sergio Botero, Sergusi, and Susie Murph. Hey everybody.
I don't actually have day pajamas.
No, you just stick with your night pajamas the whole time.
Hey, no, I have real clothes.
Yeah.
I'm wearing a collared shirt right now. Come on.
Yeah.
Look at that.
I'm it literally, I mean, again, apart from the racking grief that I feel, it feels very normal to me. It's very weird. It's very surreal, especially when you like walk outside and it's just like the weather is nice and it's very quiet.
There's a lot more people walking around outside, like where I live, which is really kind of bad for me because I have a foster dog who's super aggressive towards other dogs, and now everybody is also
Yeah.
walking their dogs, so we have like very short walks. But people are at least like taking advantage of the nice weather and getting outside that way.
But I mean, is everybody staying 2 meters apart like they should?
They are, well, I assume that the people that live together are like right next to each other, but
Yeah.
usually you see people take wide berths around
good.
each other. So
Okay.
that's,
Yeah. Yeah, we've got, oh man, what have we got? 8,500 cases in Canada now?
Wow.
Yeah. So
All of Canada, though, right?
all of
The whole-
Canada, yeah. Yeah.
Okay.
And I think we have 100 deaths.
Mm.
So it's, you know, it's not anywhere near as bad as the US, which is, I mean, I just feel so sad.
We're not doing so great over here.
No, I feel so sad all the time. And like I said, someone, you know, I definitely feel just this, you know, this just formless anxiety and grief that you then just like turn into work. So
I am very thankful my flowers in my garden are starting to bloom. So it actually gives me an excuse to go outside and do things.
Yep.
Plus, it's just like a nice little spot of happiness. amidst all of this
Yeah.
stuff.
Yeah, no, it's been just beautiful outside, and it's weird because you do forget, you totally
weird
forget. You're like,
juxtaposition.
oh, I'm trapped inside my house, but you're not actually. Like it's not like there's poison gas outside that you can't breathe. You can go outside.
Different kind of apocalypse.
Yeah. It's oh man, it's the weirdest thing. And again, it's been 100 years since human society has experienced this to this level. So. Let us move into
Crazy
the
world.
actual show. Put you all away again. There's me. Okay. Got my intro. And here we go. Hello and welcome to the Weekly Space Hangout for Wednesday, April 1st, 2020. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about Voyager 2 found another new thing about Uranus, and it's hilarious. And a new CubeSat mission to explore the sun announced. There's all kinds of interesting space conjunctions, and NASA's DART mission and the powerful ion engine that it's going to be flying with. Joining me today, I've got on my screen right now, Dr. Kimberly Cartier. Kimberly.
Hey, Fraser. Happy podcast day.
Happy podcast day.
We're already self-isolated.
Yes.
We've always been on Weekly Space Hangout.
Yeah.
That's
Once
how it
again,
works.
yeah, we're so ahead of the curve.
Many years of practice.
Yeah, we started implementing our pandemic plan with the very beginning of the show. So
We're pros.
exactly. We've got let's see, Pam Hoffman. Pam, welcome back.
Hi, thank you.
That's some good mute control. You got to talk louder. Because right now it's still just showing Kimberly.
Sure, no problem.
There we go. Where are you located again? You're in California, right?
Southern California, somewhat close to Los Angeles.
Yeah. So same thing. You've got just incredibly beautiful weather there right now.
Yes, and clearer. It's clearer because
the pollution's gone. That's lovely.
it's nice. It's
Yeah,
really nice.
that's really wonderful. Sort of a brief break until the place catches on fire.
Yeah.
And we got Michael Roderick. Michael.
Hi, thanks for having me back.
And where are you again?
Central Pennsylvania, so we're not on fire.
No, but you did
We're
just
safe.
lock down,
We did,
like
yes.
today, right?
Oh wow.
I think our county was on lockdown for a few days before the entire state.
Oh, okay.
lockdown.
Yeah, and the lockdown just happened today, so.
It's been 2 weeks here, so
Yeah.
almost three.
Yeah, you're still in the shelter in place in all of California. Yeah. No, we're a lot more loosey-goosey here in Canada. Just like stay apart. Don't leave your house much. Don't go to school. We
You might
trust
be
you.
smarter.
Yeah. I would prefer if things were a little more enforced, but we'll see what happens. All right. So before we get on to the news portion, I just want to take a second and, of course, give a big thanks to all our good friends at the Weekly Space Hangout crew. They are our friends. They are our executive producers, especially now during this time. And we have all of these guests, these astronomers and astronauts, and they're all trapped at home and they all know how to use Zoom. It is just like the perfect environment for us to bring on guests, and they are working overtime to help bring on all of these great guests. So huge thank you, of course. And if you want to be a part of this community, go to wshcrew.space. They will hook you up. You can be an executive producer too, and you can help organize more of these guests as we move through into the summer season. So let's get on with the news. And there is the interview portion. It's long. So we got about 20 minutes of news, and then we're going to shift over to the interview. All right, Pam, you're on my screen. What do you got?
All righty. Well, thanks very much, Fraser. I like to talk about stuff you can do, especially right where you are, especially now. We've got a couple of conjunctions coming up, and I would love to encourage people to start thinking about Comet Atlas. April 3rd is a big day because Mercury and Neptune are in conjunction. This is early in the morning before sunrise. And then we have a double feature, Venus and the Pleiades in the evening in the west, and Venus will be coming right through the Pleiades. Sounds amazing. Can't wait to see see that.
I'm gonna see some. I can't wait to see some pictures of Venus right in the middle of the cluster. It's gonna be really neat.
Yeah. And Venus is so bright.
Yeah, it's gonna be hard to manage the brightness of the two objects in the photographs.
Yeah, it will.
So let's talk a bit about Atlas. Is this it? Is this the naked eye comet that we deserve?
Oh gosh, we deserve one so bad.
Like Hale Bopp? How long has it been? I mean, we just keep bringing this up, and I keep hoping.
Yeah, 1997 was Hale Bopp, and it kind of was good, but not great. And what I'm looking for is something to see in the daytime, and they're talking about this one being a possible daytime at
Really
5. Yeah. Now the other possibility is because coming so close to the sun, it could just break apart.
Right. And we saw that with Ison years ago.
Okay, I don't remember, but yeah.
Yeah, Comet Ison was about, I feel like it was like back in 2012-ish, and everyone was just gearing up that this was going to be it. This was our comet of the century, going really close to the sun, so it would flare up significantly, and it flew too close to the sun.
Yeah, we hear that a lot. There is one more conjunction on April the 6th. Jupiter and Pluto are in conjunction. That's going to be in the morning too. And what I really love about these pairings is that one's really bright, which helps you find the other one.
Right. And so just for people who aren't familiar, what is a conjunction?
So a conjunction is kind of the closest approach of two celestial bodies. It could be the moon and a planet. It could be 2 planets. We've had 3 planets. There's something really great coming in December.
Yes.
Hopefully we can talk about that. But yeah, visually, and it's very much based on your perspective, because they could be, in fact, quite far apart, but we can see them as they're close together from our perspective. But yeah, so if you want to get up early in the morning and look for the bright ones, that's Jupiter and Mercury in these 2 cases, Friday, then Monday, and then that helps you like kind of a guidepost to find the dimmer ones. Which will be Neptune and Pluto, and you're probably going to need a telescope for that.
That was my next question, was just like, what kind of gear am I going to need? Like with Venus and Pleiades, obviously I'll watch Venus. You can see both with the unaided eye, so that's easy.
Right.
But with Comet Atlas, if it turns naked eye, then hooray. With these other conjunctions, with Mercury, you can see that with the unaided eye.
Yes.
And same thing with Jupiter,
right. And what I really love too with these both, the moon is going to be well set before sunrise. Sometimes we get a moon in there too, but the moon's 10 days old on Friday and 13 days on Monday, and they'll both be set well before.
I just saw it today as I was out for a walk, and I could see that it's a quarter moon right now.
Yes, first quarter.
Yeah, and so we'll see it as the sun goes down for a couple of hours, and then it will set afterwards as well. So that'll give you a pretty good sense of what you're going to see on the night of the 3rd, like on.
Yeah, and as far as observing goes, back to the Atlas, and of course anything dim, you're going to want some kind of telescope. But I was reading just before this that some amateurs have been seeing the Comet Atlas with their binoculars. So a lot of people have binoculars. That's why I like to talk about that, because they're really great for things like globular clusters.
Yeah, fantastic. Yeah, I've got a pair. Cool. I've brought on many occasions. I've got a set of 15 by 70s, which are
very cool.
Yeah, almost a little too heavy, but they're really great. You just sort of fall into the sky. I really like it. Well, thanks, Pam.
A stand or a tripod will help with that.
Yeah. All right, let's move on. Kimberly, what have you got for us?
I've got some new discoveries from a really, really old mission, because Voyager 2 is the gift that keeps on giving. And in this case, a brand new discovery about Uranus, which is one of my favorite planets because ice giants are the best. So basically, back when Voyager 2 flew by Uranus, still the only spacecraft to do that, by the way. Hint, hint.
Hint,
NASA.
hint, hint.
Hint, hint.
World
strong,
space community.
Hint, hint. Voyager 2 has a magnetometer, and as it was flying by Uranus, it took many measurements of Uranus's magnetic field, which Uranus's magnetic field is very, very strange. I think we know that Uranus is sort of fell over on its side, but its magnetic field didn't quite fall as much as the planet itself. Uranus is tilted at about 94 degrees, but its magnetic field is only at 60 degrees, which means that as the planet rotates, the magnetic field wobbles around a lot. It's very weird. We don't quite understand why. And it's a little bit misshapen too. So our best measurements of the magnetic field come from Voyager 2. And a couple of astronomers were trying to design another magnetometer for maybe eventually when we go back to Uranus. What sorts of measurements do we need and how do we need to improve? So they were going back through this old Voyager data and noticed a little 60-second blip out of 45 hours of flyby data. Literally 60 seconds of the data, and went, that looks familiar. We've seen that before. And it's a phenomenon known as a plasmoid, which is a fun word. It's a new word that I learned. Basically what that means is that the magnetic field of Uranus slowly siphoned off a little bit of Uranus's atmosphere, and then it created a little bubble supported by the magnetic field, and the bubble got pinched off and floated off into space, and is filled with ions of Uranus's atmosphere. And that's what Voyager flew through, and it has a very distinctive signature when observed with a magnetometer.
You're not telling us it farted, did you?
I am not. You noticed I did not say any of those words.
I said it.
You said it, not me.
Yeah,
but
there's
we've seen this,
no shortage of jokes that
I
people
didn't
can
say
make.
it.
People are imagining them. Go ahead,
I'm sure people are.
fill your
Do
mind with probes and gas and Uranus
I'll sit here.
and things letting off into space.
I'll just sit here and wait.
Yep,
You keep going.
Yep.
It's
Please
great.
continue with the science and everybody else.
Well, Fraser, we've seen these plasmoids on other planets that don't have as funny of names.
Yeah.
Plenty of other planets do this, but we weren't expecting to see something like this at Uranus, either back then or now. We thought perhaps that Uranus just had traditional atmospheric escape mechanisms where lighter atoms go towards the top of the atmosphere, reach escape velocity, and just sort of blip away into space. It happens to every planet. But plasmoids were a new thing that we didn't know Uranus had. And now it gives us sort of a better idea of maybe how Uranus has evolved over the past 4.5 billion years. Basically because we didn't expect plasmoids, we didn't know how to calculate for them or account for them in how the planet evolved. But now we estimate maybe like 15 to 30% of Uranus's atmospheric loss may have been from plasmoids, which is pretty neat. And the only way we'll really be able to pin that down is to go back to Uranus.
Right.
Which I feel like half of my stories about ice giants are just like, let's go back.
Yeah. I know the exact thing, which is it's shameful how little these two enormous planets in the solar system have been explored, which is once briefly.
Which I will tell you, when NASA announced its finalists for the next Discovery class mission, I literally ran around the office going, oh my God, there's an ice giant mission there. I'm so happy.
Yeah. Well, I mean, not only
really
that, but they had a couple of Venus ones as well. So
the Venus ones.
Two Venus missions and ice giant. Now, I'm all in.
So I have a 3 out of 4 chance of being really happy with their choice.
Exactly. The other one.
So is this because is it because the magnetic field is tilted differently in relation to the rotational axis, or
we're not entirely sure? Again, because this is only one measurement out of, we don't really have any other measurements to go for. This is like the one measurement we have. But it's possible that given that the planet is rotating at one angle and the magnetic field is at 34 degrees off of that, there may be a little bit more sort of force that could pull off atmosphere a little bit easier, maybe to create plasmoids, maybe. But it's like purely speculation at that point because we really only have this one plasmoid to work with. So we need more to figure out why.
Really interesting.
And we'll be watching for them, right? Because we've seen one now.
We've seen one. We're not going to be able to see it remotely because the signal is very faint. So you sort of have to fly through it with a sensitive instrument. It's not visible in like optical light or an X-ray light, and the radio signal probably would be too faint for us to see remotely at this distance.
Arjone is asking in the chat, is it like a coronal mass ejection? sort of a similar situation where the magnetic field is sort of twirling a chunk of the gas off of the planet?
My understanding of it is that it's more gentle a process than a coronal mass ejection, which is more like the magnetic field snapping and releasing a jet of particles, whereas this is more of a gentle inflation of a bubble and then it pinches off and floats away.
Right.
Is my understanding of it.
Is this a good object for like the James Webb Space Telescope to try and look for, or is this going to be way out there?
I am unsure if it emits any sort of light.
I mean, Voyager only saw it because they flew. It only saw it because it flew through it.
I'm unsure, but I would probably say no.
Very cool.
Okay.
Michael.
But it's still neat, I think.
Tell us what you got.
All right, so there is going to be a mission launching in hopefully about a year where we're going to intentionally crash a spacecraft into an asteroid. So how many people here have seen Armageddon? Hopefully everybody.
I admit, yeah, I've seen it.
All right. So the plot in Armageddon is you're gonna save the Earth by blowing up this asteroid. You're essentially just gonna put a nuke on it and blow it up. That's not very realistic if we actually want to save the Earth from an asteroid. So there's kind of two main ways that we can do it. One is that if you have a...
Uh-oh.
Did he freeze up?
Yeah, he froze up.
Uh-oh. I wonder if he can hear us still.
Well, while we wait for him to return, Kimberly, why don't we shift back to your story?
Sure.
Sure.
Oh, wait.
He's
back.
I just lost you guys.
Yeah.
Okay.
Yeah, you sort of had a glitch in the matrix for a second there. Please continue.
All right. So redirecting stuff.
Yeah.
Not doing Armageddon.
Right.
So not blowing stuff up. So you can either move the asteroid using the mass of the spacecraft to gravitationally pull it, or you can just hit it with a spacecraft, and the impact of that spacecraft is going to nudge this asteroid out of orbit, and so it'll miss the Earth. So that's the plan for this mission. It's going to launch in July 2021. It's supposed to hit what's actually a moonlet, so an asteroid that's orbiting another asteroid, and it's going to hit this thing, and they're going to look for a very, very small deviation in the orbital speed of this moonlet, about 0.4 millimeters a second. So very, very, very small change in speed. The idea then is that we're going to test this to see, is this a successful way to save the Earth from future asteroids? And so if this works, then we'll know that this is kind of the way to go.
Right.
So what's the advantage of hitting the moonlet instead of the main asteroid?
It's easier to see the effect. So the moonlet is much smaller, much less massive. And since it's orbiting some other object, you can measure the orbit of that moonlet easier than you could with some massive asteroid.
One of the things that I think is pretty exciting about this mission is they're going to be using a new kind of ion engine, an incredibly powerful ion engine.
Right. And so even, so you've probably heard of ion engines for a while. It's been in Star Trek, a lot of space lore. And the idea with these ion engines is you take some elements, in this case you're using xenon, and you essentially make it an ion, you hit it, it loses an electron, it becomes positive, and you have some kind of electrical gate at the end of the engine nozzle, and it gets pulled towards that gate, and it gets flung out of the spacecraft, and so it uses that as thrust, as momentum to push it forward. And so this engine, it has a thrust of about 236 millinewtons, which is tiny. You look at the thrust of the Saturn V rocket, that was 35 million newtons. And so this is very, very small. So the reason why we even want to use an ion engine is because they're very efficient. So chemical rockets, you got to use all this mass to boost your rocket up. Well, you can do that. You got to launch it to get into space. But once you're in space, it's much more efficient to just use these ion engines. And so this is, paving the way forward for future missions to use these similar kinds of engines.
Yeah, and these ion engines have been used. We saw it on the Dawn mission. We saw it on the Hayabusa mission. These are a very common engine now that have been in operation for upwards of 20 years in various missions. The key with this one, though, is it is the mightiest of the ion engines. I always find it's always described, the strength you feel from an ion engine is like holding a piece of paper on your hand, right? And so this is like holding a couple of pieces of paper on your hand. That's the force that it's exhibiting. But of course, the key is that you just run the thing for days, weeks, months, continuously, and the acceleration builds up over time.
Exactly.
Yeah. Very exciting. It's funny that, we know that an asteroid impact, as we are here facing an existential threat today, there are many. And we happen to be facing a global pandemic today, but we could face an asteroid impact in the future. And yet we don't know what is an effective way to try and push an asteroid off course. And so to actually have someone to actually just go and find out, try one and see what happens is tremendous progress.
It's remarkable foresight.
Yeah, it really is. Right.
We'll see if we can actually do something with the information that we get.
Yeah, so we don't need to just rely on what Bruce Willis tells us.
That's true.
Thank God.
Yeah, exactly. Kimberly, you got one more story for us.
Yes, I do. Speaking of cool missions that will launch in the somewhat near future, a new one that I just learned about today is called the Sunrise mission, which was just selected by NASA earlier this week. It stands for Sun Radio Interferometer Space Experiment, because every NASA name has to stand for something.
They need to have a backronym.
A really cool acronym. Yes.
Yeah.
Backronym, whatever.
Yeah. Well, the backronym is when you start with the acronym and then you go and then you work out the words.
They will never tell us which is which.
Yeah.
So I'll just assume that it was planned that way. But what's really cool about this mission, I think, is that it's actually a set of 6 CubeSats that will fly in tandem and coordinate to make a larger radio telescope. So that's the whole technique behind interferometry. It's something we do on the ground. And it's basically a technique of taking smaller telescopes and arranging them in such a way that when you observe the same thing at the same time, it has the same effect as if you had a really, really large telescope. So you get a much higher resolution for a much cheaper cost, a cheaper launch, and cheaper development, which is sort of the idea behind what's called these missions of opportunity from NASA. Basically, it piggybacks on some other launch.
Right.
And you get a mission to, in this case, study large solar storms.
And like the budget is absolute shoestring. You're looking at
pretty tiny.
Yeah, $62.5 million for 6 spacecraft to launch and study and act as an interferometer. Which are there any other space-based interferometers ever?
Not to my knowledge.
Not that I know.
Though
Lisa,
it's possible.
Well, Lisa's
That's
only one
thing.
though, right? So Lisa, no others have been launched yet. They just did the Lisa Pathfinder, but I don't know of another actual functioning interferometer.
Not a flying one that I know of.
Yeah.
Maybe there is that I haven't heard of.
Yeah, I'm sure someone can drop in the chat if they know one. But so that's exciting to just have an interferometer working.
And they're going to be doing radio measurements of large solar storms, and they're going to be mapping in 3D the shape of like large particle ejections from the sun, and mapping how the magnetic field extends from the sun further out towards Earth, which is something that hasn't been done before, but it's something that could really help. NASA highlighted how it can protect astronauts going to the moon and Mars, as NASA does. But it can also do things like help us predict satellite interference with our satellites around Earth, our GPS, and other satellites around Earth. And once those solar storms like interact with our atmosphere or the moon, it'll help us understand those effects a bit better too.
I mean, it's such great timing, right? You've got all these other missions that are off to examine the sun, plus you've got the Inouye telescope here on Earth, and so you've got all of this advanced new missions to study the sun, and now you got another one, which is great.
Yeah.
So,
and it's for much cheaper. It's going to piggyback on a launch that's already going, and it's going to it's predicted to launch in 2023. So really fast development as well.
Right on.
Yeah. Great.
All right. Well, Kimberly, you're on my screen. Why don't you let people know what you're working on and where they can find out more before we shift over into the interview this week?
Cool. Well, people can always find out more on Twitter at AstroKimCartier, and all of my work is published at es.org. Recently, I've been in sort of carbon mode, finding all sorts of interesting new ways that, or new science about how carbon goes from deep in the earth out into the atmosphere and how we can get it back out again.
Did you see there was like a press release that came out like yesterday or today about carbon early on in the Earth's formation was in the core of the Earth, was deep down. Yeah.
New estimates of the carbon content of Earth's core, which is still pretty tiny, but it's an important number to know for just knowing just how much carbon we have.
And that in the early formation, it started out closer to the core and found its way out, which is pretty interesting.
Well, I'm not writing about that, but maybe I will in the future.
I just assigned you the story.
I learned a very cool,
I know it's not my job.
carbon capture and sequestration method using basalts in Iceland, which is very neat.
That's right on.
Yeah, it was awesome.
It's funny, like the world is appreciating kind of a little less pollution, a little less diesel, a little less noise.
Nice.
It's kind of nice. I hope
we should keep that.
Yeah, I hope as we come out the other side of this, some of the stuff that we're doing sticks. I know that like my grocery store, it does online ordering. And before, I was talking to when I picked up my groceries today, the guy was saying, yeah, we had 15 people. Now we're hiring 50 more to catch up with the amount of orders that we're getting. And I'm sure that once we get out the other side of this and we're all so comfortable where our refrigerator just tells us how much more food we need and automatically orders it, and we just go to the store and we just, someone fills the trunk of our car and we just drive home, they're not going to want to stop doing that. So here's hoping we have less of a carbon load anyway.
Here's hoping.
Pam.
Yeah, hi.
Where can people find out more? Show us the book. There it is.
Yes, and I'm actually developing a way to get the book to people for free. So stay tuned for that.
Right on.
And
can you bring that closer to the camera so I can see the title?
Yes.
Itty Bitty.
Awesome. Amazing Itty Bitty Explore Space Now book. I love it.
Perfect for you, Kimberly. This shows you how to do all that stuff.
Yeah, I don't know how to do any of that stuff, so thanks. And I have lots of free time and a telescope.
Just remember, space is that way.
Yep. I'll drop a link in.
So helpful.
After the video's up. And I started something recently. It's Facebook Lives. Every day I'm getting on and, telling people what they can do today, that kind of thing. The conjunctions are
That's fantastic.
Yeah.
Don't you find that's incredibly good for your ability to be a science communicator?
Yeah. Yeah, much less nervous today, for example.
Yeah, exactly. Yeah, I could just tell that the practice and it was huge. Nothing changed my ability to communicate in the moment than doing this stuff live. So,
thank you very much. Yeah, looking forward to it.
Right on, Michael.
So I am on Twitter at Michael Roderick. Right now, I'm kind of stuck at home. No astronomy on tap sessions going on, so it's kind of just sitting around doing work. I do want to show off one project that I've been working on. This is a model Saturn V.
Wow.
So this is a 3D printed, and then I've been painting it. So this is how I've been doing my free time. So
wow.
That's pretty cool.
So cool.
It's a lot bigger than I thought it'd be.
Well, I guess it's as big as you scale the CAD software to be, right?
It is, yes, and I underestimated the size. Like it comes in sectional pieces, and so I thought, hey, I just make it as big as possible. You put them all together, it's like over 3 feet.
1-to-1 scale.
Could you do Astronomy on Tap online? This would be a great time to figure that out.
We've been thinking about that. I don't know that we have enough of an audience that we could.
Well, the Nerd Night people are doing it, so
I'll discuss it.
If you guys need any help figuring out the technology side of it, just let me know.
For sure.
So over on my website or on my YouTube channel, I had a live stream with Matt O'Dowd from PBS Space Time, and that was a lot of fun. He is hunkered down right in the middle of the hot zone in New York City, so he was definitely recording from his home. But if you want to watch that, that's on my channel. And I have coming up on Monday, I've got Brian Keating is returning. He is, of course, he was the principal investigator for the Bicep 2 telescope. And we're going to talk about what else is happening now that he still didn't win his Nobel Prize. and the search for primordial gravitational waves. So stick around for that on Monday. All right, well, I'm going to say goodbye to my co-hosts, but don't go anywhere because we have an absolutely fascinating interview, which you're going to want to watch. So
Thanks, Fraser.
everybody say goodbye.
See you later.
And we will shift to the interview.
Bye.
Thanks, guys. All right, here we go. I'm wearing like exactly the same thing, even though we recorded this interview like a week and a half ago. Incredible. All right, here we go.
Nuclear engineering at North Carolina State University.
All right, joining us today, we've got Robert Hayes from North Carolina State University. Rob, thank you so much for coming on the Weekly Space Hangout.
My pleasure.
So who are you? What do you do?
So I teach nuclear engineering at North Carolina State University. We now have a new minor in health physics. Just submitted the paperwork to also have a graduate certificate in health physics, which is actually the discipline of radiological protection. So we study how to protect, how to characterize, assess, and mitigate the effects of ionizing radiation, whether that's from external exposure where you're doing dosimetry versus internal where you're looking for characterizing radiological content in the air, aerosols, radioaerosols, things of that nature. Or just assaying things that somebody might eat or drink using standard radiation detection scenarios. But one of these recent things that we've done was we did a little bit of research in some shielding concepts.
Yeah, and I definitely want to talk to you about that. But I think that, like just the general topic is of dramatic, great interest to people who are fascinated about space exploration because the levels of radiation exposure out there in space, once you get out of the Earth's protective magnetosphere, even when you fly on an airplane, they get higher and higher the farther away you get from our protective planet. What are the sort of the different kinds of radiation risks that we need to think about when we're, say, performing some kind of deep space flight, like, say, going to the moon?
So going to the moon, you basically, once you leave the atmosphere, then you're subject to the solar wind. And that has a dependence on where you are relative to the Earth's poles. That's where you get the aurora borealis, is the solar wind coming down the magnetic field lines. And so outside of that solar wind, which you're going to have from here to the moon, you also have cosmic ray particles. The cosmic ray particles are very different. They're very, very different. The solar wind is mainly protons being accelerated from the sun and impinging on the atmosphere. But with cosmic ray particles, you can have things all the way up to iron, where you have highly ionized nuclei that are very energetic, that can literally punch a hole through the shell of a spacecraft and punch a hole through you.
Right.
But it's at the atomic level, so it's not something you could feel or you would be able to tell if you've had these occur. You actually need instrumentation to see that. Possibly the exception is if it goes through your eye.
That's what I was about to say. Yeah, I
Right.
recall astronauts saying that if you close your eyes, you can see the cosmic rays hitting your your various optic nerve, and that feels a little unnerving.
They do get irradiated up there.
Yeah, they do, for sure. And then, of course, there's also the trapped radiation that is swirling around the Earth through the Van Allen belts and things like that.
Sure.
So if you were to sort of describe, I mean, I think you already sort of got there, but if you were really to describe the sort of the levels of the threat, how would you rank them? Trapped radiation, solar wind, cosmic rays. Which one is put them in order of scariness?
So the worst is going to be the cosmic ray particles in terms of dose per event, because it's got something that's called a very high linear energy transfer. So the amount of energy that's deposited per unit length that it travels is going to be the highest. But it actually, because you only have a relatively fewer number of those, it doesn't necessarily give you the highest dose depending on where you are. So if I'm taking a flight, say from China to England over the poles, I'm going to get a substantially measurable dose because I'm going through that solar wind, the northern lights. I'm going to be up in that area. Whereas if I'm in deep space, it's at a lower dose rate, but per event, it's a higher per event. It's just you have fewer events. So there's a play that you have between the two. If I'm spending a lot of time in deep space, depending on where I'm at, one can be more than the other.
And I mean, you get the situation where you can have really powerful solar storms deliver years worth of cosmic rays dose in an hour if the storm is bad enough, if your timing is bad. So I guess it's one is kind of inevitable, like time just slowly catching up with you, and then the other one is could be bad luck if you happen to be out in space. Both, I guess, are trouble. Now, I mean, you talk about the kinds of when we're down here on Earth and we're worried about, say, a nuclear reactor exploding and releasing particles, and we think about radiation, how is that kind of radiation and sort of the risks associated with that different from the kinds of exposure in space? Because, here on Earth, I'm kind of imagining particles that stick around in my body and do damage, while out in space it's sort of like these one-time exposures that I don't have to worry about any kind of long, it's not like it's trapped in the spaceship with me.
All right, so I think that was maybe a 20-second question, and it's going to take about a 3-minute answer.
Oh, good.
Okay.
That's fine. That's right. Because I mean, the point is I think that when we think about space flight, we do imagine this radiation, but a lot of people, they don't see it as sort of, or they don't understand the difference really between that and, say, the risks we're worried about here on Earth. So that's okay if it's a 3-minute answer.
Okay, so what we do in our discipline for radiation safety is we have this thing, it's called an equivalent dose. It's where we normalize the dose in terms of risk. And when you do that, there are a number of factors that you have to take into consideration there. One of those is actually something I already brought up, a linear energy transfer. Something that has a high linear energy transfer has a higher dose weight when you come up and calculate this equivalent dose. Something that's just simple like gammas or betas, just simple electrons, those are going to have the lowest weighting factor, because in terms of the amount of damage, tissue damage that you do per energy deposited is going to be different between the two.
Right.
And so you have these weighting factors for these different types of radiation. You also have a dose rate factor that takes place. So if you get a big acute dose, like from the atomic bomb survivors, that gives you a certain radiogenic cancer risk later in life. But if you get it spread out over a long period of time, it's substantially reduced.
Right.
Your body is able to basically repair itself.
Right.
If it's spread out instead of having having an acute exposure. Then on top of that, you have specific tissue weighting factors, so that the lens of the eye has a different sensitivity than the skin, than the muscle, than the bone, than the bone marrow. All of these have different sensitivities to radiation. Basically, it's a function of how complicated it is and how fast those cells reproduce. So like your digestive tract, where you're continually digesting it, those are reproducing themselves very fast. Mm-hmm. And so they're going to be more sensitive than cortical bone, which doesn't reproduce itself very fast. So that's less sensitive, versus bone marrow, where you're producing red blood cells on a regular basis. And so those are very sensitive. So all of these things get weighted together to come up with an equivalent dose.
Right.
And so once you weighted those together, then that equivalent dose is how you would be able to calculate risk. For example, if you wanted to look at cancer risk, it's about on the order of about 5% per sievert or per 100 rem. So if you get an acute dose of a sievert or 100 rem, your normal lifetime cancer risk of about 40% would now go up to about 45%. Right. If you got a big dose like that.
Yeah.
Now that's a really, really big dose. The dose that they're looking for, I think what you might be thinking about is the Mars trip, where they're looking at getting it, say a quarter of that. So that quarter of that is your lifetime dose from the Mars trip, but then that might raise your probability of cancer by 1% or 2%.
Right.
But then that becomes rather irrelevant, because if they're doing I say that in the sense that most people don't care, because I know a lot of people would do a one-way trip. And if you're doing a one-way trip and you've got a 1% increase in cancer from the radiation dose, I don't think you're worried about the dose.
Well, there's also the problem that Mars doesn't have any magnetosphere. So as soon as you get down, get out of your spacecraft and and you're on the surface, the clock continues to run. But
yes, if you're unshielded, absolutely.
Yeah. So then, what are the mechanisms that are the best protection for radiation in space?
Oh, that's a great question. So it's going to depend on what you're looking at. So if, for example, if you're doing a Mars trip with nuclear rockets, then you've got the shielding from the nuclear reactor that's propelling you, right? If you're looking at just the cosmic rays, then the issue that you have there is that based on a cost-weight ratio, your craft is largely going to be aluminum, which means it's got a low Z, a low atomic number. And so a low atomic number is not very good at shielding high LET particles like cosmic rays.
But it's better at lower energy particles, like things coming from the sun and things like that? Is there sort of there's like a place where it works really well and then starts to not work so well, right?
So it's not so much that the aluminum wasn't chosen as much for the shielding properties as it was for the cost, the strength per weight that you can get. And so if you're looking at like a beta particle, it's great. It's fantastic for just an electron. For the photons, not so much. For neutrons, not again. For the protons, it'll work pretty good. But again, it's going to depend on how much energy you have. Right. So a typical solar wind isn't going to be too much of a problem. But if I have some that are relativistic from, say, cosmic ray particles that are relativistic, they're just going to go straight through the entire crack.
Right.
So it's going to be a function of that energy. So LET is part of it, but also the energy, because the LET is also a function of energy.
Right. Right. And so then, we talk about aluminum and other things, but at the end of the day, isn't it just protons? Like we're just trying to get as many protons between us and whatever is coming our way?
You could look at it that way. What ends up happening is that the protons, if you're shielding the protons from the solar wind, then you're going to be getting rid of most of it because you don't really want to shield for the cosmic rays. It's just not practical to do that. That's just something you've got to eat. If you're going to be in space, it's the amount of weight you would have to get effective shielding for that is just going to be prohibitive to lift it up into outer space.
Well, let's say, SpaceX is launching the Starship and they're just blasting big blocks of lead into space. Like how much shielding would you want to actually effectively block cosmic rays? If you wanted no exposure whatsoever, how much are you looking at?
No exposure whatsoever? So
pretty much, like Earth level exposure.
Earth level exposure. Yeah. Oh, I'd actually have to do that calculation. I wouldn't be able to do that off the top of my head. My initial feeling would be that you're not doing proper risk management if you're looking at it in that perspective.
Right.
There's a certain amount of risk you get from radiation, but the biggest risk is really that you don't make it back or that you lose air or those are the biggest risks.
Right.
And so you need to do a risk management approach where you're looking at all risks in total and then lower them all together.
Right.
So
one option that I've heard quite a bit that a lot of people like, maybe in the far future as we get better in harvesting resources out of space is to use things like water. That water works well as a radiation shield.
Yes, it would.
Surround your spacecraft in a block of ice and,
if it's the water that you have to use anyway.
Which you have to use anyway, drink. But you just require, I've heard, like a meter is good.
Yeah, that'd be good.
Yeah. Just surround the Orion capsule in a straight meter of water. All right. So you and your team have worked on some ideas to try and, not encase perhaps a spacecraft in meters of lead, but instead a way to sort of shave down the weight profile and volume. So can you talk about the research that you did?
Yeah, so what we actually focused on was not the problem of shielding for the astronaut per se. It was making sure that the astronaut or a satellite or some other piece of electronics would be able to survive a large radiation field. So for example, if you had, for example, a solar flare event, and let's say that you got a big massive dose, again, the cancer is only 10 or 20 years out. If an astronaut, say they got a full 100 rem, then as long as they made it through the acute radiation syndrome and they survive, which they'd have a reasonable chance of that, then they've only increased their lifetime cancer risk of 5% over the normal 40%.
Right.
But if they lost their electronics, it's over anyway.
Right.
It doesn't matter. It's all game over at that point.
And
well,
so sorry, just to clarify that then, like one of those acute events has a serious chance of frying the electronics on your spacecraft. Like at a certain point, it gets pretty bad.
It can.
Yeah.
So the what I had mentioned for biological sensitivity, there's a similar rule that applies to electronics. So the more detailed that it is, if you understand solid state theory for semiconductors, when you're looking at the interface where you have the depletion region for any kind of a nonlinear circuit, and I start generating electron hole pairs in there, I'm going to compromise its ability. And that's what you get from just the gamma rays. If I get a high LET particle, or even say a neutron that can come in and start creating structural damage in there.
Just banging out pieces of the wires. Not
the wires as much as it is the silicate.
Right.
And that's in that circuit, say an integrated circuit. And so if I compromise a few of the transistors or a few of the diodes in that circuit, it might not work anymore. And unless you have a new chip to put in there, then whatever that was doing for your spacecraft is not going to do it in the same way anymore. And if it dies, then again, game over.
And I mean, we see this kind of an issue with, say, spacecraft that are sent to try and survive in the Jupiter environment, and a lot of the risks, or a lot of the decisions that have been made have been to keep your spacecraft as far away from Jupiter as possible and fly by Jupiter for the minimum amount of time possible. So does this technique both sort of help with, say, trying to survive some kind of solar storm, but also being able to just kind of get closer and be around places like Jupiter for longer?
It does, in the sense that really all that we did was something that was rudimentary simple. It was to provide a higher shielding worth for a lower weight.
Yeah, and so talk about this idea.
Okay, so if I'm going to put a PC board, say, on a missile or rocket and send it up, then it has to go through a whole bunch of vibration and shock, right, and still be able to work. But when it does do that, it has to be able to do it in an environment that may have some very strong thermal gradients. And if that occurs, then I can get from any kind of residual material that's in there, some deposition or evaporation. And you can get funny things on top of that, like whiskers, where you get these small little metallic growths on some of the metallic leads. You can't have any kind of evolution. You can't have deposition of any kind of water vapor or anything, or any kind of dust. So basically, it's a long way of saying you really want to have that thing hermetically sealed. And so what we do is, to hermetically seal these, is you'll take the PC board when it's all assembled and it's been tested and verified, and you dip it in like an acrylic resin, like a shellac or a polyethylene or something like that. It's actually none of those, but it's basically the same concept.
Right.
And now then you let it drip dry, and now it's hermetically sealed, so that nothing can get in or out or evolve on that PC board. So a traditional concept of a shield, a radiation shield, is where I surround something, or I surround the radiation source with some kind of an attenuator material. Now, if you just think in the most basic terms, if I were to try to shield something, let's say my phone, and I were to put, say, a 1 millimeter thickness lead shield around it, if I were to put that out at 1 meter and make it a spherical meter shell, it's going to be a lot more lead than if I put it down at 10 centimeters.
And yet still provide essentially the same amount of
shielding.
Protection.
Right. But if I then took that 1 millimeter of lead and I coated my phone with it, it's substantially less again.
Right.
And so that's the approach that we took, is to use that coating. However, We couple that with something that's a little, it's familiar but different. If you think of an aggregate in concrete, right? The aggregate is just a bunch of rocks.
Right.
Or
sand
if I
or
look
whatever, whatever you want to make your concrete with.
Right, some sand, some rocks of different sizes. So that basically it's like a brick house in that the bricks are the rocks, but you just got a bunch of cement for fill. Right, and that's how we do concrete, it's how we do brick houses. And so the idea was to do something similar with the conformal coat. That's what that layer is, the goop, the plastic goop. You do the same thing with the conformal coat, but you don't want to do that with a traditional shielding material like lead or tungsten, because if I did that, then that would be conductive. And now I'm introducing into the circuitry area, up close and personal to the circuitry, a conductor.
Yes.
And that can change its inductance, it can change its capacitance, it can do some bad things unless you really design the circuit to handle that.
Right.
So in order to prevent that from happening, and on top of that, if we did that, if you were to put into the conformal coat actual metallic bits, the metallic bits are quite expensive. Tungsten metal is very expensive. So it would be gadolinium, so it would be erbium.
Right, and so these would be metals that would be non-conductive, but provide shielding and be able to work with this resin that you're talking about.
So not quite. So those metals are conductive.
Okay.
All of those metals, if I have it in the metallic form, they are conductive.
Okay.
We don't want to have a conductor up close and personal to this PC board unless it's designed for that.
Yep.
So rather than redesign the PC board, we do the same thing that we had with the conformal coat. It's an insulator. It's a good insulator. Well, another really good insulator is metal oxides, rust.
Yeah.
And so what we looked at is we came up with this idea. I wonder if this would work, that if we put rust in a conformal coat, that if you had it as an aggregate, if you put this rust in there as an aggregate into the conformal coat, that you could get a higher shielding worth per volume, even though you're introducing a little bit of oxygen in there. The oxygen that you put with the rust is just displacing the conformal coat material anyway. So it's really not a penalty in terms of the mass or the volume, but you still get that metal in there on top of it. But now it's conformed. So it's as thin and as close as you can get it up to that circuitry.
Right.
And so the metal gives you a good attenuation property for all of the low LET materials. The conformal coat, that gives you a good attenuation for the low Z materials, the protons and the neutrons, because those are going to, if they interact, they have a good cross section to interact, and they have a very small range as a general rule. If I get a recoil event taking place, if I have a recoil, if I have a neutron, on average, a neutron that would interact with a proton in that shield will lose about half its energy per interaction. And so what you want to do is you want to get those to rapidly get their energy down below where I am approaching the energy threshold to actually cause an interstitial. That's actually a low threshold, but the key is that does this provide better shielding than a traditional aluminum box for the same incident field?
Right, and so in the traditional method, you would have your electronics, you may seal them, but they're going to be inside an aluminum box, and you're providing, and the box has all the dimensions, as you said, you're a much larger object with a lot of empty space. And so you would envision then having your electronic parts, wrapping them in this layer, and then having them unshielded beyond that point. So you're not having to use any of that additional shielding weight.
Correct.
Right.
So that, you've already got a weight and volume penalty for the conformal coat. You've already swallowed that. We put in a little bit more weight by having in this aggregate, but it gives you a much bigger bang for your buck in terms of the shielding worth. That was the idea, and that was what we published.
And just to, just as we sort of wrap this up, then you found that you were able to sort of, using this technique, you were able to reduce the overall weight by as much as 30% for the same mass, right?
For the same amount of shielding work.
For the same amount of shielding, yeah, for the same amount of shielding protection, you could do this with 30% less mass.
At worst case, yes. For the lower energies, it gets a lot better. But what we looked at is we looked at neutrons and photons with a uniform distribution of the photons, but for the neutrons, we looked at a prompt fission distribution. So the idea is that not only does it apply for space applications, but if you want to do nuclear hardening, we actually evaluated that as well.
Right. And if you were to sort of imagine then, I mean, I'm just imagining some future spacecraft, some mission to the moon or lunar base or whatever it's going to be. And as you said, these are mission critical pieces of electronics. They must stay online all the time or people start gasping for air. How powerful of a solar storm would you see wanting to be protected against? How much shielding can you imagine people wanting to sort of put into their electronics?
So now I put on my engineer hat again. It depends on what your design specification is. So you would actually go to, say, someone from NASA, and you'd say, what is the largest credible dose that this could get and for this mission? And then they would give a dose specification. And so you would say, so I've got to have an incident radiation field that will give me that dose. Now I have to build a shield that will match that.
Right.
And so that would just come up with a certain thickness that you would have to come up with to mitigate that particular dose.
But just to give us a sense, like what is, I mean, are we talking microns? Are we talking millimeters? Are we talking, is it does it feel like a bubble wrapped circuit board, or does it look just like it, but with like a thin sheen to it?
So I can't actually answer that question, but what I'll do is I'll answer a different question and you'll tell me if it still answers that question.
Sure, yeah.
So without knowing what the specification is, what we were able to show is for any specification that you come up with, if you replace the old shielding configuration with our new shielding configuration, you get that benefit, 30% less mass for the same shielding work. So once you came up with what that worst case would be, so let's say you wanted something that was in an orbit around the pole where you're going to get a massive dose, then that would have to have a higher design spec than something that was, say, maybe it was going out to look for some comet out in the Kuiper belt or something. I don't know.
Right. I'm just sort of imagining, the electronics and whether they would just be sort of this amorphous blob of rusted metal is how it would look, and you couldn't even see the circuit board anymore, or whether it would just be, almost transparent. The coating would be so light, but obviously it depends on the spec. I'll put my spec together and I'll send it to you for my human mission to the moon, and we'll go from there. Rob, absolutely fascinating work, and it really shows like there are a million details that need to be worked out as humanity takes this next step into exploring and really becoming a true civilization spanning, sort of solar system spanning civilization. And it's these little details, right? There's 1,000, there's 1,000,000 of them, each one that someone's got to sit down and think about and work out and engineer and develop prototypes and test them in space. And it's great to, I really enjoy kind of the nitty gritty of the work that's being done to make this happen. So thank you so much for taking the time to share your work with us. And I hope that you can protect both astronauts and their electronics in future missions.
Always getting better.
Where can people find out more if they want to keep an eye on the work that you're doing?
I have a website at NC State. What is the
Yeah, we'll put that in
address?
we'll put that in the show notes of the show so people can click on that if they want to find out more.
Okay.
Excellent. Well, Robert, thank you so much for taking the time to chat with us today here on the Weekly Space Hangout, and good luck with your research.
Thanks. Bye-bye.